At the end of last class, we started an example of a rational function as a refresher.
Oh, no, I think our class from over there is not here yet.
I know, where are they? They're on their way. I saw her erasing. So we'll start from scratch with rational functions. We'll define them, and we'll do some basic graphs. And by the end of today, you'll be masters at graphing rational functions. So a rational function, they're on their way?
There's a whole group in there.
All right. -1, -1. Oh, wait, you guys were doing math?
Yes.
+1, +1, +1. So a rational function is just a quotient of polynomials. Polynomial in top, polynomial in the denominator. Cube or cube. They're functions. And if they're functions, they have to pass the vertical line test. That's a really important thing. They're functions. Pass the vertical line test. Let's take a look at some. So 1 over x, that's probably the simplest rational function of them all. That graph is actually called a hyperbola. It's a tilted hyperbola. You learned about hyperbolas in 121 or somewhere. That's a tilted hyperbola. And it has an asymptote along the y-axis, a vertical asymptote. And 1 over x also has a horizontal asymptote along the x-axis. So it's got 2. And when we're looking at the denominators, last class we talked about there being a vertical asymptote wherever the denominator is 0 as long as the numerator is not simultaneously 0. So if we look at these, the denominator here is 0 when x is 0. That's why we have a vertical asymptote along the y-axis. Denominator here is 0 when x is 0. So same argument. That's why we have a vertical asymptote along the y-axis. Here, the denominator is 0 at -2 and +1. And the numerator is not simultaneously 0, so both of those are vertical asymptotes. Now, let's take a look at these three also, I guess. Factoring the denominators here allow us to see those vertical asymptotes. I'm just going to focus on the denominator here for these guys. So the denominator here is 0 when x is 3, and 3 doesn't make the numerator 0, so we have a vertical asymptote at 3. This guy here, if we factor the denominator and the numerator, there are no common factors, so the zeros of the denominator are vertical asymptotes at -1 and +2. And then a vertical asymptote over here at -1. So vertical asymptotes, it's probably the easiest piece. You look in the denominator, you find the zeros, and as long as the numerator is not simultaneously 0, you have a vertical asymptote. All right. And an important feature of a vertical asymptote is that it's never crossed. The graph cannot cross a vertical asymptote. Now, last class I mentioned that rational functions will have one or more vertical asymptotes, and then they have another asymptote. And that asymptote, that other asymptote, is either a horizontal line, a diagonal line, or it could actually be a whole nother function. It could be a parabola or something else. It will have some other asymptote, and the form of that other asymptote depends on the relationship between the degree of the numerator and the degree of the denominator. In college algebra, usually they have this little table and they say, if the degrees are equal, then you have a horizontal asymptote at the quotient of leading coefficients. So if the degrees are equal, you have a horizontal asymptote at the quotient of leading coefficients. Right here. So these two examples are examples where the degree in the numerator and the degree in the denominator are the same. And what is the quotient of leading coefficients here? 1. 2 divided by 2. And that's why there is a horizontal asymptote here at y equals 1. Right there. What is the quotient of leading coefficients for this second one? Also 1. And that's why there is a horizontal asymptote at 1 there. So if the degrees are the same, you have a horizontal asymptote at the quotient of leading coefficients. If the degree of the denominator is greater than the degree of the numerator, where is your horizontal asymptote? At 0. So if the degrees are such that the degree of the denominator is larger than the degree of the numerator, you get y equals 0 as the horizontal asymptote. Right there, let's make sure. Okay. So those are the two ways you have a horizontal asymptote. If the degrees are the same, the quotient of leading coefficient. If the degree in the denominator is larger, then the x-axis is a horizontal asymptote. All right. So, can horizontal asymptotes be crossed? Yes. So verticals, no. Horizontals and slanted and general oblique asymptotes, yes, they can be crossed. Okay. And you can see that over here, at least theoretically, it kind of looks like they're trying to imply that the graph of that's crossed right there. So how would you find out where or if a horizontal asymptote is crossed? So right here we have that y equals 0 is a horizontal asymptote. How would I know if that asymptote is crossed by the function f? How could we figure that out? We're really asking the question, do the function f and the horizontal asymptote, which is a function also, f of x equals 0, how would we decide whether two functions share a point? Which is what we mean when two functions are crossing, they're sharing a point. And so if we think of the x-axis as a function, y equals 0, how would we decide whether two functions cross or not? What do you do to them? Huh? Just because the Cubs won the World Series doesn't mean that you don't have to answer my questions. What do you do? How do you tell if two functions intersect? Set them equal. Set them equal, right? That's a system. If you have two functions and you want to know if they cross, that's a system. You just set them equal to each other and see, oh, is there a solution or not? So if we want to know whether this function and this function, horizontal asymptote is a function, if we want to know whether they cross, we just set them equal to each other. So in this case, we are setting it equal to 0 because that's what the horizontal asymptote is. So if we set 0 equal to this function, we can then multiply both sides of this equation by the denominator, and we get that x is equal to 3. So it does cross there. So that's the general way to figure out if a horizontal asymptote or an asymptote in general is crossed. You set them equal to each other. Now in this particular case, that's also an x-intercept. So we would have found this anyway, because when we're looking for x-intercepts, we're looking for the zeros of the numerator that are not simultaneously zeros of the denominator. So zeros of the denominator, vertical asymptotes. Zeros of the numerator are x-intercepts, as long as there's not common factors. Okay, so we know about these horizontal asymptotes now. Here, there's an oblique or a slant asymptote. This book, every example that I've looked at, I don't think I saw any. I haven't seen any other examples where the other asymptote is anything except a slanted line. So in this book, they always call it a slant asymptote. But it could be different. So there's a slant asymptote there. And the question is, how do we find it? And the hint is that it's not dissimilar from what we did for these two guys. Really, what we did was divide the denominator into the numerator. And when you divide x into 1, you get 0. If the denominator's power is bigger than the numerator, when you try to divide, you get 0 as your quotient, and then you get a remainder. What about here? If you do long division, 2x minus 6 into 2x plus 5, you get 1. That's the quotient, and then there's some remainder. And that's the general process. If you want to find the other asymptote, just divide. And it will find horizontal asymptote of 0. It will find a horizontal asymptote quotient of leading coefficients. And it will find the slanted asymptote. Just divide. In college algebra, they set up those three things. Here, just think of it as division. No matter what the other asymptote is, just divide, and you'll find it. So if you just do division, and in this particular case right here, we could use synthetic division, but this time I'll use long division. We could use synthetic division because the divisor there, the denominator, is linear. What times x gives negative x squared? Negative x, so that's negative x squared minus x. And now we have to remember that we're subtracting. This minus this is 0, and then up here we have a placeholder of 0x, and we're subtracting negative x, so we get plus x. And then what times x is x? 1, and now we're done. As soon as we get to the constant, the quotient is the asymptote. The quotient is the asymptote. So our slanted asymptote, in this case, is y equals negative x plus 1, which is that thing right there. All right. Now, if we want to know whether it's crossed or not, what do? Set it equal to the function. If we want to know whether the asymptote, which is a function, crosses the function f, we set the two equal and see if there's any solutions. So if we want to decide whether there's crossing or not, we would set negative x plus 1 equal to the function, negative x squared over x plus 1, and we'll see, is there a solution or not? If there's no solution, it's not crossed. If there is a solution, there's a crossing point. Multiply both sides, so we get negative x squared. I'm foiling here. Right? Negative x squared, and then plus x and minus x cancel, and then plus 1 equals negative x squared. Add x squared to both sides. 1 equals 0. Are there any solutions? No. 1 is not equal to 0. Therefore, no crossing. The asymptote is not crossed. No crossing point. Okay? So if we set the asymptote equal to the function, we can find a point of intersection if there is one. All right, so in summary, vertical asymptotes occur where the denominator is 0 as long as the numerator is not simultaneously 0. And what happens if it's simultaneously 0? You get a hole. Yep. You get a hole. Vertical asymptotes are never crossed. Horizontal and slant asymptotes can be crossed, though. Okay, so the other asymptote, again, it's horizontal if the degree is the degree of p, that's the numerator, is less than or equal to q. If the degree of the numerator is bigger, then the denominator can actually divide into the numerator, and that quotient is the asymptote, the other asymptote. And again, this book, they're all slants. But if the degree of the numerator was, say, 5, and the degree of the denominator was 3, when you divide a polynomial of degree 3 into a polynomial of degree 5, what would your quotient be? Polynomial of degree 2. 2. 5 minus 3 is 2. Everyone agree? So if you have a degree 5 in the numerator, degree 3 in the denominator, when you divide, you get a quadratic. So that will give you a quadratic asymptote. But this book doesn't have any of those, so you don't have to sweat that. You don't have to deal with 5 minus 3. Okay. So the other asymptote, again, is found by doing the division. It's just the quotient. As soon as you get to the constant in that long division, you're done. Horizontal or slant may be crossed. All right, so let's go ahead. And the instructions here say just find the asymptote. They don't say to graph. So let's just find the asymptote here. And it doesn't even, the instructions here are just for the other asymptote, the horizontal or the slant. If we wanted to figure out the verticals, we would set the denominator equal to 0 and solve, factor it or whatever. Let's just do what the instructions say. Now, if you don't want to remember that whole power business, you can always just divide. If you remember the power business, that's totally fine. You say, oh, the powers are equal, so it's the quotient of leading coefficients. Doesn't matter. It will always work if you divide. If you divide, it will always work. Okay, so divide the denominator into the numerator. What times 2x to the 4th is 8x to the 4th? 4. Done. That's the quotient. As soon as you get to the constant, you're done. And because the powers are equal, the quotient is simply going to be a constant. And our conclusion then is that y equals 4 is the horizontal asymptote. And again, if you know the power thing, and you say, oh, the powers are equal, the horizontal asymptote is that the quotient of leading coefficients, which is 4. This one over here, we could use synthetic, but let's do a little practice with long, because there are some problems here where you definitely will need long. And as we're going, it should be kind of obvious that we're going to get a line. If you take a quadratic and you divide it by a linear, you're going to get a linear. So we're saying what times x is x squared? That's x. And then here, remember you're subtracting. If you need to, put parentheses and a minus sign if you need to. One thing I wouldn't do is this. I see a lot of mistakes where, and a lot of teachers do teach you this. They say, oh, just come down here and change the signs. And that works, but if you have some error later when you go back, it's really hard to sort of figure out what you did, unless you use a different color. So the thing I'd like to do is put parentheses around it. If I want to do something extra, I do that. And then do the distribution in my head. X squared minus x squared is 0. Negative 6x plus 5x is negative x. All right, and then x times what is negative x? Negative 1. Done. Don't go any further. As soon as you get to the constant in your quotient, you're done. And so that tells us that y equals x minus 1 is a slanted asymptote, a slant asymptote. Now let's check in both these cases whether they're crossed or not. So this book also doesn't do a lot of deep analysis of this process, but let's just do these two just to make sure that it's clear. So if I want to know whether that horizontal asymptote is crossed, I set the asymptote equal to the function and then look for a solution. So we set asymptote equal to function. And let's put a question mark next to cross. So it's a question. Is the asymptote crossed or not crossed? So we set the asymptote equal to the function. We cross multiply. So we get 8x to the fourth minus 40 equals 8x to the fourth plus x minus 2. Subtract off the 8x to the fourth. Oh, look, we're getting an x value. So if we solve for x, we add 2 to both sides, so we get x equals negative 38. So that means that the asymptote is crossed. So it is crossed. So this implies this was an HA. So HA is crossed at 38, comma, how do we find the y value of the crossing point? And do we have to plug it into anything, actually? Because the horizontal asymptote, it's y equals 4. Right? So all the y values along that horizontal asymptote are 4. And we're crossing it, we're checking to see whether a horizontal line is crossed. So we know the y value is 4. So there's not much to plug in there. That's the smartest place to look. You could absolutely plug it back into here also, and you would end up with 4, but that would be a heck of a lot more work, right?
Did you have your negative on the 38?
Oh, thank you. Yeah, negative 38, comma 4. Thanks. All right, so that's a crossing point. Now over here, same idea. If we want to know whether this slanted asymptote and that function intersect, if they share a common point, we set the asymptote equal to the function. Asymptote equal function, and see if there's any solutions. Okay, so we cross multiply. X squared minus 1x minus 5x, that's minus 6x, plus 5 equals x squared minus 6x. Subtract x squared from each side, add 6x to each side. We end up with 5 equals 0. That's not true. So that implies no crossing point. So that tells us that this slant asymptote, x minus 1, is not crossed by the function. Any questions on that? So that tends to be the hardest part with rational functions, finding the slant asymptote and deciding whether it's crossed or not. That tends to be the hardest part. All right, why don't you guys do number 30? And again, just deal with the slant asymptote or the horizontal asymptote. We'll do the complete rational functions in a minute. So figure out your other asymptote. Did you watch that last night? Oh, that was crazy.
That was terrible. I was sweating.
I know. My wife saw something on Facebook that said, "Oh, I'm sick of this election coverage. It's driving me crazy. I'm going to go watch some relaxing baseball." And then that game was so nutty. Let me know if you have any division issues. get that slant asymptote, we divide the denominator into the numerator. Can you use synthetic division in this case? No. That denominator is quadratic, so we can't use synthetic division. So we have to do long division. Denominator into numerator. It's a slant asymptote. We have to go all the way out to the constant. It's not just the quotient of leading coefficients here, is it? You have to divide this entire denominator into the entire numerator. You can't just chop off that stuff. So you can't look at just the denominator. You have to hold it. Yeah, that's right. Negative goes up there because you're putting up here a quantity that multiplies by the 6x squared to give you 12. Oh, no. Should be no minus there. Now I understand. It's just exactly what's equal to. So you're saying what? The number that goes, the quantity that goes here times that equals 12x cubed. And that's plus 8x. And then the thing to remember is that we're subtracting this from this. 12x cubed minus 12x cubed is 0. Minus x minus 8x. Good? And then, okay, so then, squared, so we'll be done then?
Right, but when you subtract, you want to subtract the 12
minus 9x, and that doesn't go with it. So then we're done.
Right.
Yeah, so as soon as you get to the constant may be 0. As soon as you get to the constant, you're done. That's your OA, or your SA is this book. So it should be, ahead of time you kind of acknowledge that the degree of the numerator is 1 more than the degree of the denominator. So that's telling you that, okay, I'm going to end up with a slanted line for the asymptote. So we ask ourselves, what multiplied by 6x squared gives us 12x cubed? And that would be 2x. That's the quantity when multiplied by 6x squared gives us 12x cubed. And then 4 times 2x is plus 8x. And then here's where we have to remember we're subtracting off that whole quantity. 12x cubed minus 12x cubed is 0. Minus x minus 8x is minus 9x. And then can 6x squared go into 9x, minus 9x? No. Right? So we're done. That's it. So our conclusion is that our slant asymptote, and it's a slant asymptote because this is a slanted line, is y equals 2x. It's important to put the y in there because it's a function. It's a line. All right, try one more. Try 32. And same heads up at the beginning. You say, okay, degree of top is 1 more than degree of bottom, so I should get a line. I should get a slanted line. Looks like saw lots of 5x's right here, so that's the first step. That's great. When you multiply this across, you get this, and you have to subtract. So the 5x cubes obviously will cancel out. That's why we picked 5x. And then we have negative x squared plus 5x squared. So that's 4x squared. And then for the x's, we have x minus 10x, so that's minus 9x. So what's the next term in our quotient? Plus 4, done. Don't even have to multiply it out. We're done. As soon as we get to that constant, we can draw our conclusion that the slanted asymptote is y equals 5x plus 4. All right, so now let's do that extra step. Again, the book doesn't emphasize this, but let's just do it because it's important. Let's figure out if either of these is crossed. So it's a question, is it crossed? So again, you're thinking of your asymptote as a function. You've got your original function f, and you want to know, do they meet? So two functions meet if they share a point, and to find that shared point, if there is one, you set them equal to each other. So here we're going to set 2x equal to 12x cubed minus x divided by 6x squared plus 4. Multiply both sides, cross multiply here. So we get 12x cubed plus 8x equals 12x cubed minus x. That gives us 9x equals 0. X equals 0. So this tells us it's crossed at 0, comma, what? 0, comma 0. If you go back into either the asymptote or the function and you plug in 0, you're going to get 0. So it's crossed at the origin. This is a crossing point that we would have picked up anyway by finding x-intercepts, because that's also an x-intercept. So we would have figured this out, even if we didn't test this extra piece. Because we would to find the x-intercepts, we would have factored the numerator, and we see that x equals 0 is a factor of the numerator. All right, how about this one? So 5x plus 4. Set it equal to the original function. I guess I could grab it from right there. Okay, so we cross multiply. It's a little messier because we have a binomial and a trinomial, so we multiply them together. We have 6 terms that have to add up. So we'll just do it step by step. We're going to take the 5x and multiply it across, so we get 5x cubed minus 5x squared plus 10x. So that's 5x being distributed across this polynomial. And then we have to distribute the 4, so we get 4x squared minus 4x plus 8. And that's going to be equal to the numerator on the right. And then we have to combine like terms and see if we have a solution. 5x cubed, subtract away. Let's look at the x squareds. So minus 5 plus 4 is negative 1x squared. And on the right, there's a negative 1x squared. So those are all going to wipe out. And then on the left, we have 6x. 10 minus 4 is 6x, and we subtract 1x there, so we have 5x on the left. So I've combined the x's. And then on the right, I'm going to put the constants. So on the right, I already have a negative 1. On the left, I have a plus 8. I'm going to subtract the 8 to the other side, so I get negative 9. So this tells us that we do have a solution. That says that the asymptote and the function meet. They share a point. And that shared point has an x coordinate of negative 9/5. And how do we find the y coordinate? Is it easier to plug it into the function or to plug it into the asymptote? Yeah, plug it into the asymptote. That's always going to be a little easier because we're always dealing with a linear function at most over here. So plug negative 9/5 into there. The 5's cancel. We get negative 9 plus 4, which is negative 5. Right? Negative 9 plus 4. All right, so that's its crossing point. So let's see if we can put it all together. So let's start from scratch, do the full process here. So the full process, we need to find all the asymptotes. We need to find all the intercepts. And that's it. All right, so generally, almost every book is going to start with the vertical asymptotes. We again look for where the zeros of the denominator are, and these are lines. So it's best to write the vertical asymptotes as x equals a constant, because that's the equation of that's a line. If you just put a number, if you just write 0, it's not clear. You want the line x equals 0. Okay, and then this is going to have a horizontal asymptote. Can you see what the horizontal asymptote is? Yeah, y equals 3. Because the degrees are the same. Numerator degree is 1, denominator degree is 1. Now, if you didn't see that and you just follow the principle that I mentioned a few minutes ago, just divide and you'll find the other asymptote. If you were to take x and divide it into 3x minus 1, x times 3 is what gives you 3x. And then we're done because we've made it to the end of the quotient. If you get to the constant, you're at the end of the quotient. So y equals 3 is the horizontal asymptote. All right, let's check whether the horizontal asymptote is crossed or not. So we set the asymptote equal to the function. Bless you. We get 0 equals 1, and is it crossed? No. Then we go to the intercepts. So asymptotes first, and then intercepts. X-intercepts are where the numerator is 0. And in this case, there's only one 0 for the numerator, and that's what? So the x-intercept is an ordered pair. It's a point. We should write it as 1/3 comma 0. It's an ordered pair, that intercept. It's a point. And then we go for the y-intercept. For the y-intercept, we're plugging in x equals 0 to the function. Oops, can't plug in x equals 0. It's a vertical asymptote. So this tells us that there's no y-intercept. Right? Because when we plug in x equals 0, it's undefined. We have a VA there. And VAs are never crossed. So no y-intercept. Now we're ready to graph. Yeah, Richard?
I just want to be clear, so
Sure.
because it's the same degree, we know that's a vertical asymptote.
Because these are the same degree, we know it's a horizontal.
Oh.
The horizontal at y equals 3 That's because the degree of the numerator is 1, the degree of the denominator is 1, and 3 divided by 1 is 3. That vertical one comes from the denominator being 0, and the numerator is not simultaneously 0, so that's a VA then. And now we're ready to graph. We are ready to graph. So, first let's graph our asymptotes. So we'll put our VA on the graph. Our VA is x equals 0. That's the y-axis. And then we had y equals 3. So we'll do that. And then our x-intercept, we only have one of them. And that's at 1/3, 0. Right there. All right. We now know exactly what the graph looks like. We need no other information. When you're looking at this, my suggestion is to think of the vertical asymptote as separating the plane. So if we look to the left, we've got this vertical region here. And there's only two choices. The function has to approach each asymptote. And there's only one way it can approach each asymptote. It has to look like this, or it has to look like that. There's only one way. If we're down here in the lower region, it has to look like that. And if we're in the upper region, it has to look like that. But it's a function, so it can't be both. It's got to be one or the other. And which one does it have to be? The upper region or the lower region? Upper. Why? Because there's no x-intercept right there, right? There's no x-intercept, so it can't be down there. So process of elimination tells us that this cannot be the graph down there. It has to be just this upper arch right there. That's it. Okay, then we go to the next vertical region. And again, there's an upper possibility and a lower possibility. And in this case, it has to be the lower possibility because we have an x-intercept that we must go through. So that would be our graph. Do this one. So over here, vertical asymptote at 3. That's where the denominator is 0. And the numerator is not simultaneously 0, so it's definitely a BA. How about a horizontal asymptote? Or slant asymptote? What would the other asymptote be? Well, to find the other asymptote, we have to look at we have to compare the powers, or we think division. And what would the quotient be if we tried to divide this denominator into the numerator?
Vertical asymptote, it's 3. It seems to be like a positive number because it's to the second power.
But what's 3 minus 3?
0. Just do that first. Okay.
So we do that first. 3 minus 3 is 0, so we have a 0, and then 0 squared is still 0, and that's in the denominator. So if we have a 0 in the denominator, we have something that's undefined. Right? And that's what creates the vertical asymptote. We have a fraction that's undefined. That's what creates the vertical asymptote. So the horizontal asymptote? 0. Is everyone clear on that? So to get the other asymptote, we have to look at the powers. In the numerator, the power is 0. In the denominator, the power is 2. And if the power in the denominator is larger, if you try to divide, you get 0 for your quotient. So you can either acknowledge that, oh, degree of denominator is larger than the degree of the numerator, so therefore we get y equals 0. Or you just try to do the division. And if you multiply that out, x squared minus 6x plus 9, and you try to divide that into -2, it just doesn't go in. Right? So then we make our conclusion that y equals 0 is the horizontal asymptote. And then we should test whether it's crossed or not. And is this one crossed? No way, right? Because if you multiply both sides by that denominator, you get 0 equals -2. Not true. So it's not crossed. Okay, then we go for our intercepts. Is there any x-intercepts? No. Right? For an x-intercept, the numerator has to be 0. Because an x-intercept is where the y values are 0. To find where the y values are 0, you set 0 equal to the function, which we actually already did right here. So if we set 0 equal to the function, there's no solution there. The only way this function can be 0 is if the numerator is 0, and the numerator is never 0, because it's always -2. So the numerator is not 0. All right, so no x-intercepts. How about a y-intercept? For a y-intercept, we're plugging in x equals 0 to see where the y-coordinate would be. And we plug in x equals 0, we get... Here, we get an answer, for sure. What do we get? Yeah, -2/9. So that's our y-intercept at -2/9. Okay, so now we're ready to graph it. So we're going to plot what we know. We know the y-intercept is 0, -2/9. Right there. We know there's no x-intercepts. And then our asymptotes, we have y equals 0 and x equals 3. So y equals 0 is there. And x equals 3 is right there. All right. Now here, we actually don't have enough yet. We are going to need one tidbit of information in a moment. And that's because over here on the right, we need some extra information. We don't know, in this vertical region here, we don't know if we're going to have the upper arch or the lower arch. We don't know. Because there's no extra information. Like over here on the left, we know. We know that it's going to look like that. Right? It has to approach both asymptotes. It has to go through that y-intercept. There's no crossing point, so it has to be that. The only other option would have been up here, but it can't be up there because there's no y-intercept there. So it can't be up there. But now when we jump over here, we do need a little bit of extra information. There's only two choices. It's either this upper arch or this lower arch, one or the other. Can't be both. It's one or the other. It's a function, so it can't be both. So let's see. Let's plug 1, 2, 3, 4. Let's plug 4 into our function and see if it's positive or if it's negative. If the function value is positive, then we have this upper arch. If the function value is negative, we have the lower arch. So all we have to do is test f of 4. And we don't really care what the y value truly is. We just need to know if it's positive or negative. That will tell us whether we're in the upper or lower region. Well, denominator is always positive. Numerator is always negative. So that means this function is always negative. So it has to be the lower arch, not that one. So that's our graph. Okay, any questions on that? Asymptotes and intercepts. And if necessary, a test value. So here we had to pick a test value. Let me just write that here. So we needed a test value, and we chose x equals 4. That's not how I want to say it. Test value at x equals 4. test value showed that the function was negative there. So that's how we knew it was the lower arch. Okay. Another one. Let's see, I'll do this one because this one's weird. This one you guys can work on, but let's do this weird one first. Okay. We always start these things with vertical asymptotes. This is a rational function, by definition, is just a quotient of polynomial. So it is a rational function, but it's not going to have all the same features that we traditionally think of as part of a rational function. Are there any VAs here? So the VAs are where the denominator is 0. Is the denominator ever 0? No. Denominator is never 0 there. So there's actually no vertical asymptotes here. So this is not going to be what we tend to think of when we think of a rational function. Typically, we're thinking vertical asymptotes and these little arches all over the place. So no vertical asymptote there. How about a horizontal asymptote? Y equals 1/3. The powers are the same, so we look at the quotient of leading coefficients. Or you do long division. 3x squared into x squared is 1/3. That quotient will be 1/3. Okay. How about x-intercept? Let's see if it's crossed or not. So we set the asymptote equal to the function. And the more you do this, you start to see, especially if this is a constant here, we're going to be multiplying it over. So I'll do that in one step. I'll multiply that. I'll bring that denominator over. So we're trying to figure out if this equation has any solutions. So if we multiply that out, we get x squared plus 2/3 equals x squared minus 2x minus 3. So we do have a solution here. I'm going to add the 2x to the left, subtract the 2/3. So we're going to have minus 9/3 minus 2/3, which is minus 11/3. So here, x is equal to negative 11 over 6. Okay, so it is crossed. Yes, it's crossed. And it's crossed at negative 11 over 6. And what's the y coordinate? 1/3. All right, so it is crossed. Okay. X-intercepts is next. So we go asymptotes and then intercepts. X-intercepts, let's see. So we have to factor the numerator. And x-intercept is where the function is 0. The only way the function is 0 is if the numerator is 0. So let's take a look at the factorization here. So that's x minus 3 multiplied by x plus 1. So we have two x-intercepts, 3 and negative 1. So 3 and negative 1. Y-intercept can't be more than 1. Y-intercept, we go to our function, we plug in x equals 0. A y-intercept is the place at which x is 0 along the y-axis. And what do we get? Plug in 0, negative 3/2. So 0, comma, negative 3/2. All right, let's see what we get. Plot what we know. Three comma 0, negative 1 comma 0, 0 comma negative 3/2. That's about right there. And then we had a horizontal asymptote. We had no verticals. We had a horizontal at 1/3. So there's x equal or y equals 1. to a horizontal asymptote at a third. So something like that. That looks more like a half, but you get it right there. Then we had a crossing point. That horizontal asymptote was crossed. That was crossed at x equals negative, almost negative 2, not quite to negative 2. So there is a crossing point right there. All right. Now that's plenty of information to get a decent sketch of the graph. Now there's some things we don't know that, again, you'll learn in calculus. But we definitely have to approach this asymptote on both sides. The left tail and the right tail have to approach. And the way that this crossing point works, whoops, stay over there. The way that crossing point works, we're coming up through the graph, up through that asymptote, but then we have to dip back down. We have to approach that asymptote. So if we cross an asymptote, then we turn and come back down and get super close to it. Now over here, there's some ambiguity. There's going to be a relative min, and we don't know where it's at. We don't know if that relative min is, let's try to sketch that a little bit cleaner. The relative min, we just don't know exactly where it's at. So we can get, like, this could dip down and then come way down here, or it could turn quickly. That we just don't know. So don't worry about it. So it's going to come down through that and then up through there and over. Something like that. So now what we traditionally think of as a rational function. It's like a bunt. It's not really a egg. Okay, let's go to a more traditional rational function. Bang. All right, you guys do that one. Much more traditional. Where the denominator is 0, as long as the numerator is not simultaneously 0, so factor. Factor first. Factor. You should be finding two vertical asymptotes. That denominator factors pretty nicely into two linears. So where are your linears? Yeah, you got Face palm.
Well, that's what X equals.
High five to the forehead.
I know.
Well, up here we don't have X.
So your factoring should look like that. So I've got the asymptotes up there if you, hopefully you've gotten that far. Now, that asymptote is the x-axis, so you don't really have to check whether it's crossed or not because you're going to figure that out later when you find x-intercepts. You don't have to do both. You can do one or the other. Right? The x-intercepts are going to be crossing the horizontal asymptote necessarily.
No, you're good.
Or the
So it's
x-intercept.
X. Because this is saying is a constant equal to this.
Anyone have an asymptote question or an intercept question? Yes.
Right. So there's
No, that's when you find the y-intercept. So you said x equals 0 to find the y-intercept. To find the horizontal asymptote, you divide the denominator. Because the degree of the denominator is larger,
no, don't give up.
you can't divide it in.
So you're going to set this whole problem equal to 0.
Yeah.
And then what you want to do to get rid of the subtraction is multiply.
Yep.
Denominator by this.
Always, yep, exactly. The denominator's power is bigger, it's
Yeah.
always y equals 0. Exactly.
Which, if you multiply everything by 0, 0, but then you still have your numerator there. So you know that equals 2.
One x-intercept, there's only one place where the numerator is 0. And then your y-intercept, 0. That's where you plug x equals 0 when you're finding your y-intercept. And minus 2/15. So that's everything we need to know. Whenever the x-axis is an asymptote, sometimes you have to pick a test value, depending on what's going on. So we may need a test value, but don't pick one until you know you need it. No need to do extra work unless you know you need it. All right, so x-intercepts at -5 and 3. Y-intercept at -2. Oh, no, not -2, -2/15. That's a tiny number in there, tiny magnitude, super close to the x-axis. Stay right there. And then our asymptotes, VA. Oh, what did I do? I plotted the VAs as x-intercepts. Those dots should not be there. Oops. Those are supposed to be vertical asymptotes. Come on. There we go. That's better. Okay. And then horizontal asymptote along the x-axis. All right. So we had one x-intercept. That was at -2. Okay, so that's what we have going into the graph. So there's not. Let's focus on the middle region because that's a little different than some of the other stuff that we've done. We have to approach both asymptotes here. The only way we only have one x-intercept, so the only way we can approach what's down below is arcing to the right here, like that. But here, do we know whether we cross the x-axis at that x-intercept there. Could be a touch or a cross, right? Right, touch or a cross. How did we determine whether x-intercepts were touches or crossed? Multiplicity. If we went up and looked at that 0 right there, what's the multiplicity of that 0? Just 1, right? There's no parentheses with the power, right? It's just the multiplicity is 1. So that's odd. So is that a cross or a touch? Cross. All right, so we have to approach this asymptote. We have to cross right there. And then we also have to approach this asymptote. So we have to approach both those. That's the only way we can do it with a 0 that has multiplicity 1. Okay. Now let's get to our other vertical regions, the one to the left and the one to the right. We definitely need test values. We need a test value because we don't know whether we're arcing above or arcing below. So we're going to need a test value. So test value, actually we'll need 2. So let's see, 1, 2, 3, 4, 5. So -6. We're going to plug in x equals -6. And then we're going to plug in x equals 1, 2, 3, 4. Those are our test values. And we don't care exactly what the y-coordinate is. We just need to know whether it's positive or negative. That will tell us. So let's go up to our function, plug in -6. Right here where it's factored is probably the easiest place. If we just care about the sign, -6 in here in the numerator is negative, negative, and negative. So if you take 3 negatives and you multiply them together, you get a negative. So that tells us the function is negative when we move out at x equals -6. So that means that our arc is down below. So we must be down here. Because that test value gives a negative. So that's what this thing here is. That's a negative sign right there. Now let's plug in x equals 4. Don't need exactly what it's equal to. If you look right here, you can just deal with signs. Plug in x equals 4, positive, positive, positive. And that's all we care about is whether it's positive or negative. So this is positive down here. So that tells us that our graph is up above, that it's this upper arch or arc. Make sense to everyone? Sorry? Yeah? All right, let's take a break there and finish up chapter 4 after the break. The important thing about a whole is that we need to look at the factorization of the original function, and if there's a common factor, there's going to be a whole instead of an asymptote. And we can simplify the original function, but we just have to remember that the domain from the original function comes from its original presentation. So -2 is not in the domain. So if we look down here to the simplified form, this is true as long as x is not equal to -2. Okay, so a lot of books will call a hole in the graph a removable discontinuity because it's just one point that's missing. So if there's just one point that's missing, sometimes I call it a removable discontinuity. Okay, so let's graph this one right here. Graph these two guys. So it's important to factor because you can't tell unless you factor whether there's a hole or not. This numerator here factors into, looks like +1 and -3. All right. So what we see is that this also is a rational function that doesn't really have the same characteristics that we would normally associate with a rational function. Is there going to be a vertical asymptote? Yes or no? Right? Because that's a common factor. So no vertical asymptote. How about a horizontal asymptote? And what would that horizontal asymptote be? Is that wishful thinking? So why would you say there's a vertical asymptote? I mean a horizontal. To have a horizontal, the powers have to be either equal. If the powers are equal, you would look at the quotient of leading coefficients. Or if the power in the denominator is bigger, you would get the x-axis as a horizontal asymptote. So you're not going to get a horizontal here. You're going to get slanted asymptote, right? Slanted asymptote because the degree of the numerator is 1 more than the degree of the denominator. So to figure out that slanted asymptote, it's a little weird here, because if we were to do the division, we can cancel this common factor, and the division's giving us x minus 3. Okay, so we are going to have a situation where this is, because of this hole, the asymptote and the function are essentially the same. When we do this division here, we're going to get just x minus 3. All right, so it's more of a philosophical thing. Do you consider it an asymptote when it simplifies like this and it doesn't? We don't really care. We'll just call it an asymptote. So then we go to do our graph. And the graph, let's find our intercepts first, I guess. Intercepts x, are there any? 1, 3. How about a y-intercept? Any y-intercepts? What do you plug in to find a y-intercept? So you plug in 0 and you get negative 3. All right, so that's what we have. So this function simplifies to just x minus 3. And what is the graph of x minus 3? It's a line. The only problem is that we have a hole. Oh, and I didn't write hole down over here. Let's write the hole down. Usually we write it right in between the intercepts and the asymptotes. Usually. Put it up here somewhere. So the hole was at negative 1/2. So we know there's a hole at negative 1/2. Now we have to find the y-coordinate of the hole. And to find the y-coordinate of the hole, you plug that x value into the x right up there. So you take the simplified form of the function and plug the x value in there. So that's going to be minus 1/2 minus 3. So that's minus 1/2 minus 6/2, so minus 7/2. So that's going to be where our hole is. All right, then we go for our graph. So negative 1/2, negative 3.5, that's down here. That's the hole. And the slope of this is 1. We have the y-intercept of 3. We have the x-intercept of, or excuse me, the y-intercept of negative 3. And our graph will look like a line with 1 point removed. So a punctured line. That'll be our graph. So it's kind of superfluous to refer to the x minus 3 as also an asymptote, but technically when we start with a rational function, we would call it an OA or an SA. All right, let's take a look at that one. Try that one. Number 68. Make sure you factor first. It's the only way you're going to see your holes is if you factor. many VAs are you coming up with? Huh? How many? 1. Right? Got it? Everyone see 1 VA? X equals -1. And how about a whole? Whole is a point. Let's put it as an ordered pair. So 3. So that factor can cancel out. And to figure out the y value of the whole, you plug in the 3 into what's left. So you're going to have 3 times 2 is 6, plus 3 is 9 divided by 4. That's going to be the whole.
Where'd you get the 3? Is that from the x minus 3?
Yep. So the zeros of the denominator that are also zeros of the numerator. So common factors. Common factors give you wholes. What do you get for your horizontal asymptote? 2? The exponents are equal, so we look at the quotient of leading coefficients. Or you can do the division. And notice that you can do it in either the original function or the reduced function. If you look at the reduced function, the numerator and denominator both have a degree of 1, and the quotient of leading coefficients is also 2. So it doesn't matter where you look. You can look at the reduced one. Anyone get an x-intercept? What's the x-intercept? Close. Negative 3 halves. Yeah, negative 3 halves. Right. Negative 3 halves. Good. So we set the numerator 0 to 0. The numerator 0 to 0. The numerator factor to 0. And then how about a y-intercept? What do you get? So we're plugging in x equals 0 to get that y-intercept. And we get 3. And again, you can plug into the reduced function. If you plug in 0 into the reduced function, you get 3 over 1. Or you can plug it into the original. Doesn't matter. The original and the reduced are exactly the same, except there's a hole in the original. So now we're good to graph. Okay, so let's plot what we know. We have a horizontal asymptote. Where's our vertical? Our vertical is at -1. Let's plot all these asymptotes. -1, y equals 2. Let's graph our whole 3 and 2 1/4. So that whole it's definitely above the horizontal asymptote there. X-intercepts -1.5, 0, and 0, 3 is our y-intercept. Now, that horizontal asymptote, we never actually tested to see if it was crossed. Let's test that real quick just to make sure. The only possibility is if it was, well, I guess it could be crossed in a couple of places. Let's just check. I forgot to check that up here. So we want to check whether our HA is crossed. I'll squeeze it in right here. So to test whether it's crossed, we set the asymptote equal to the function. And when it's totally fine to set it equal to the reduced function. So we're going to set it equal to the reduced function. And are there any solutions there? If we multiply both sides by that denominator, we get 2x plus 6 equals 2x plus 3. 6 equals 3. No. So it's not crossed. Just to make sure. Okay. We need no test values here. We have everything we need. To the left of the vertical asymptote in this vertical region, we only have two possibilities. We have an arc up here, or we have an arc down here, and it has to be the lower arc because of that x-intercept right there. Over here, we have two possibilities, an arc down here or an arc up there. It has to be the upper arc because we have the y-intercept in the hole, and there's no points down there. So that's our graph. Yeah?
Would you get the x plus 3 on the bottom of the chart?
Checking whether it was crossed or not. So when... That's a great question. It's supposed to be x plus 1. I'm setting the asymptote equal to this reduced function, and the reduced function is 2x plus 3 over x plus 1. Yeah. No idea how that turned into a 3. Sorry. Thank you. Good catch. Excellent catch. That should be 2x plus 2 right there. 2x plus 2, and 2 is not equal to 3. Yeah. Thank you. Any other questions on that? All right. Let's move on. Time for some sign charts. Remember sign charts? No? Oh, good. This will be nice and fresh. It'll be like the first time you've seen sign charts. It'll be so exciting. Okay. So, let's consider the inequality that we want to solve here. This is already factored for us, and that's going to be an important step, is to have the left-hand side factored and the right-hand side be 0. So these first two are already set up pretty nicely for us. This one already has a 0 on the right. This one's not factored, but it's easy to factor. So that's going to be a first step in solving these linear inequalities. And then what we have to do is set each factor equal to 0 to find the 0. Okay. Here's how we're going to do it. So we're going to put x plus 3. We're going to stack. We're stacking our factors. And then we're going to look at a number line. And we're going to pluck off these 2 points that are the zeros of the factors. So -3, -3, and plus 5. And those are the only numbers we're putting on this number line. Those are 2 transition points where the sign of this expression might change. The only way the sign of this whole expression is going to change is if the sign of one of the individual factors changes. All right, so here, and we're looking at signs because all we care about is where is it negative. So we're trying to figure out where that whole expression is negative. All right, so here's how our sign chart works. We stack our factors, and then down below, I'm going to, well, let me start going first. So to the left of -3, we pick a test value like -4. Plug in -4 into both of those factors, we see that each are negative. And then a negative multiplied by a negative is a positive. So I'll put the result down below. I'll put an R for result. In the middle, between -3 and 5, obvious test value, 0. Doesn't matter, pick any number in there, but 0 is a pretty good one to pick. So this factor here, if you plug in 0, that's positive. Plug in 0 there, this factor is negative. Multiply, and you get a negative. To the right of 5, both are positive. Result, positive. Now we can answer the question. The question said, for what x's is this product negative? Well, we look at our sign result here, and our result is that from -3 to 5, the result is negative. Let's do this guy over here. So we stack our factors. We create a number line where we mark off the transition points. And by transition points, I mean the zeros of the factors. Those points are where the sign could transition from plus to minus or minus to plus. Put our result down below. Pick a test value to the left of -2, like -3. Both of those are negative. The result is positive. When you multiply two negatives, you get a positive. Test value between -2 and 3. Again, it doesn't matter. Any integer between there will work. Plug in 0. That's kind of the easiest one. And then out here, both are positive. All right. So the question here said, where is the result greater than 0? So the result is greater than 0 from -infinity to -2 union 3 to positive infinity. That's where the result is positive. Nope. You don't include because the inequality is strictly greater than 0. So you want to know where it's positive, not positive or 0. Where it's strictly positive. Okay. Ready for a harder one? So this one is a little bit more complicated. It's certainly not set up in the way we had the other two set up, so we have to make that happen. We have to make the right-hand side 0, and we put everything else to the left. So subtract the 5x, and we get -x. Subtract the 9, we get -2. And then we have this. We factor it. Okay, we stack our factors. We've got our result. We build our number line. Our transition points on the number line are the zeros of the factors. So that's our setup. Everything to the left and factor. Stack your factors. And now we pick test values. To the left of -1, like -2. Negative, results positive. Between -1 and 2, pick 0. Negative, positive, result is negative. To the right, they're both positive, so the result is positive. Now here's where we have to do something a little different than the last one. This inequality is a compound inequality. It's greater than or equal to 0. So we have to treat it a little differently. So we certainly, for positive, we have these two regions. So we're going to go -infinity to -1. But instead of using a parenthesis to exclude -1, we have to use a bracket to include. And then union 2 to infinity. And a bracket on 2 also to include it. So if we have a compound inequality, we have to consider those endpoints. Bracket is including. Parenthesis is excluding. Same process here. So with this one, our setup is going to look super similar. Everything to one side and factor. When we stack our factors, we find our transition points and put them on a number line. And then we're going to pick some test values. And the pattern on these ones is, it's pretty obvious. We'll have some that are going to get more complicated very soon. Test value in the middle. The result. Test value out to the right. They're both positive. So then here, the big difference, again, is the inequality symbol. It's not a strict inequality, it's a compound inequality, less than or equal to 0. So when we look at our negative region here, it's negative or 0, so we include those endpoints. So our final answer is going to be bracket -1, bracket +1. So we want to include both endpoints because of that compound inequality. Are sign charts coming back to you? Have you done them before? Never. Did you do college algebra here?
No, I didn't.
I think they're supposed to cover up college algebra. Okay. All right, you guys try these ones. And then we'll get to the harder ones. Got to have the basic procedure down before we can do the harder ones. So. Yeah. Does it not factor? It doesn't factor?
If there was a positive 8.
Who picked that one? Ugh. So what do you have to do then? How do you find the zeros of quadratic formula? Oh, I didn't mean for it to be that complicated, though. You're welcome. Should we just change it to a positive? All right, let's just change it to a positive. Let's keep it simple. We know that you all know how to use the quadratic formula, so let's not bother with that. Yeah, Jess could sing the quadratic formula song for us. There. Yeah, there we go. That's better. That works. No, don't sing it. Oh, that song? Yeah. There's some weird mess up. What's that? Oh, to a gal? The square root song? Quadratic means quadratic formula. To a gal, that's not bad. It's a lot better than you. That's a lot better. I don't see a minus sign up there. What are you talking about? Nice catch. We don't need to go to the quadratic formula. Yeah, that's a lot better. All right, so is everybody okay with that setup then? Does that look right? And then to the left of 2, do we get negative and negative? So if we plug in, say, 0, 0 is to the left, we're going to get a negative and a negative. Between 2 and 4, pick 3. 3 minus 4 is negative. 3 minus 2 is positive. To the right of 4, pick 5 or 10 or 100. Both are positive. So our result, positive, negative, positive. And it said, where is x greater? Where is that result greater than 0? So we should say negative infinity to 2, parenthesis, union 4 to infinity. Piece of cake? Or questions?
So you're just picking random values, right?
Yep, just a test value in that interval. So when we're in the interval to the left of 2, you can pick 1, you can pick 0, you can pick negative 1, you can pick negative 10. So any number that's over to the left of 2. And then in here, any number between 2 and 4. You can pick 2.5, you can pick 3, you can pick 3.5, and then over here, any number greater than 4. Yep, that's right. Any other questions you're not sure about? All right. That one, factors. Do one more of these, and then we'll go to Then we're going to go to rational inequalities, where we have a rational function. Factor that by grouping should work. Scream if it doesn't. Two groups. Pull the GCF out of each group. Then you'll have a common binomial factor. Yeah, X squared. Good. That's right. You factor it?
Yes.
Grouping? So what's your what's the GC? Yep.
Yeah.
We did it earlier this semester. Right? We did it.
So don't think that these numbers are negative on the number line. It's just what numbers make that equation true. Or yeah, positive or whatever it needs to be. Yeah. Yeah. Oh, okay.
Just good.
Yeah, so if you put out a negative 4,
You'll be fine. Oh. Decisions. decisions. What to do with life,
Yeah, yeah.
other than playing video games and watching TV. Okay, so factoring by grouping, we factor the GCF out of our groups. We end up with a common binomial factor of x plus 1. That jumps all the way to the front, leaving us with x squared minus 4. And let's factor that on the fly. X squared minus 4 factors into x minus 2 and x plus 2. All right, then we stack our factors. We build our number line. And on the number line, the only numbers on our number line are the zeros of our factors. So those are the numbers where the sign could transition from plus to minus or minus to plus. And then we have 4 intervals here. We have 4 sub-intervals, and we have to pick a test value from each one. And it doesn't matter what your test value is. It just has to be in the interval. So to the left of -2, we could pick -10, whatever you want. And we see that all 3 of these factors are negative if you pick a negative number to the left of -2. The result is then negative. If we have 3 negatives, they multiply to a negative. The next subinterval, we have to pick something fractional, so maybe -1.5. Plugging in -1.5 here, we get a negative. -1.5 here, we get a negative. How about there? Positive there, right? We plug in -1.5 there. All right, so then the result is positive in that interval. Then we go to the next interval. We could plug in 0. 0 is between -1 and 2. So then we get plus minus plus. To the right, plus plus plus. So that is our sign chart. And then we have to go back up and look. Do we want to know where it's positive, where it's negative, and do we include the endpoints? All right, so we include the endpoints and we want positives. So our conclusion down here, we include the endpoints. So it's -2 to -1, including endpoints. Union 2 to infinity, including the endpoint on 2. So that'll be our result. Good? All right. So now let's up the ante a little bit. Up the ante. So now we have a rational inequality as opposed to a polynomial inequality. So we have a rational function, an inequality symbol, and same kind of setup. We want to get everything to the left and 0. And we want, ideally, well, we need to have it set up so that these are combined into one fraction. If it's combined as 2 like this, it's not going to help. We need one fraction. So let's just compare, let's just look at a simpler one here first. So the numerator is -2. That's a factor. That doesn't change sign, but that's one of the factors. The denominator is the other factor. And then we have our result. And we're going to set up our line. There's only one 0. There's only one transition point, and that's 5. It's the only place we have to look. Now, -2, isn't that always negative no matter what? That's not going to change anything. It's always negative. It's not going to change based on x. But here, this changes, right? If we're to the left of 5, it's positive. If we're to the right of 5, it's negative. So our result then is negative, positive. And the goal said find the x's for which this expression is greater than or equal to 0. So what should our final answer then look like? Should we put a bracket on that? All right, so let's think carefully. If we do put a bracket on 5, we're including 5. But what happens if we plug in 5 into this fraction? Division by 0, it's undefined. So that means that in this case, even though we have a compound inequality, our instinct is to put a bracket on it, but that doesn't work in this case because this 0 is coming from a denominator. So with a rational function, what we're going to see is that we're only going to bracket zeros that are in the numerator. Zeros in the denominator are going to cause it to be undefined, so we don't bracket those. Okay, so we're going to only bracket numerator zeros. And one thing that you can do, one thing that I like to do as I'm going through these, as I'm getting my zeros here, if I have a 0 that's from a denominator, a lot of times I'll stick a little x through it just to indicate to be careful there. That's a bad one. That causes division by 0. It's not in the domain. All right, let's go over to this guy. So here, what we have to do is get a common denominator. And the common denominator is going to be the product of the two denominators. So we're going to multiply numerator and denominator of the first fraction by x minus 1, numerator and denominator of the second fraction by x minus 2. Then we'll have a common denominator. So we have to turn it into a single fraction with multiplication all over the place. Multiplication and division. So here in the numerator, we'll have x squared minus 1 minus the quantity x squared minus 5x plus 6. Leave the denominator factored. We need everything factored. Okay, so the numerator is going to simplify to, let's see, what? X squareds are going to go away. So we're going to have 5x minus 6 minus 1, so minus 7. All right, so there's our final factored rational expression. All right. So we're going to stack our factors. We have 5x minus 7, we have x minus 2, and we have x minus 1. What? Uh-oh, where did I go? I have no idea how I jumped that far. Okay, so there's our line. And we're going to put our zeros on that line. So 2 and 1, and what about that 0? What's that one? 7/5. So that's 1 and some change. All right, so 7/5, 2, and 1. Does that look good to everybody? 3 zeros. So here's what I would do to just keep it in my head that the 2 zeros in the denominator, those are bad. Those can never be included, right? Because they cause division by 0. But this one could be included. So that's what I would do just to remind myself as I go through the problem that 2 of the zeros could never be included, 1 could be. Now let's pick our test values. To the left of 1, obvious choice is 0. Get negative, negative, negative. That result is a negative. I'm going to use a different color so it doesn't get messed up with those guys. So negative, negative, negative. That's a negative. Between 1 and 7/5. So 1 is 5/5. So we have 5/5 and 7/5, so an obvious choice would be 6/5. So if we plug in 6/5 right here, 6/5 times 5 is 6. 6 minus 7 is negative. 6/5 here. 6/5 is 1 1/5. And if you subtract off 2, that's definitely going to put you in the negative territory. Here, 6/5 minus 5/5 is 1/5. That's positive. Negative, negative is positive, times positive is positive. Then we have to pick a number between 7/5 and 10/5. So let's pick 8/5. Plug in 8 over 5 right there. The 5's cancel. 8 minus 7 is positive. 8 over 5 is 1 3/5. 1 3/5 minus 2 is negative. 1 3/5 minus 1 is positive. And then out to the right, all three of those factors will be positive. Okay, so the question said, when is this expression negative? So negative, we're going to go negative infinity to 1, union, and we'll deal with parentheses and brackets in a second. So we've got that. Those are the two intervals where we have negative values for that expression. We look, though, and the inequality is strict. There's no equal to piece. So we definitely are just putting parentheses everywhere, because there's no equal to piece. So it's going to be that. All right. Now, if that was less than or equal to, so let's just put an extra note here. So if it was less than or equal to 0, then we would have negative infinity to 1. We would not include 1 because that causes division by 0. Union. 7/5 is okay, though. It's a 0 from the numerator. So we would put a bracket, 7/5 comma 2. 2 has to be excluded, so a parenthesis on the 2. So if there was a compound inequality, we would include just that one endpoint. Any questions on any steps? A little bit more complicated than the polynomial ones, but still very procedural, not too crazy. All right, let's take a look at 62. Our process is always the same with an inequality. With an inequality, you have to get everything to one side, and you have to turn it into multiplication and division. Because if it's multiplication and division, you know two negatives combine to a positive, and a positive and a negative combine to a negative. So we've got to get it all to one side, factored, a 0 on the right, so we can just compare signs. So this one, we subtract off. The whole right side, we subtract it over, so it looks like that. We must get a common denominator. Don't make the mistake of saying, oh, x minus 7, x minus 9, x plus 2, x plus 3. You cannot do a sign chart from there. It has to all be multiplied together first. The common denominator is the product of the two. So I'm going to multiply x plus 3 times the numerator over here. So that's x squared minus 7x plus 3x is minus 4x minus 21. And then we're going to have a minus, and we multiply that denominator times that numerator. So we get x squared plus 2x minus 9x is minus 7x. 2 times minus 9 is minus 18. So when we combine, so now we have to combine those two numerators by distributing the minus. So just remember that this minus is right there, and it's got to be distributed. When we multiply the top here by x plus 2, that minus has to distribute across. So just don't lose it. So that numerator becomes minus 4x plus 7x, that's positive 3x. Constant, we have negative 21 plus 18, so that's negative 3. And the denominator is x plus 2 and x plus 3. Greater than or equal to 0. So you have a choice right here. You can factor out the 3. You don't have to. But factoring out the 3 is a possible step. You could just use 3x minus 3 as your factor. But if you want to factor it out, you can see the 0 a little more easily. Doesn't really matter. So now we stack our factors. Do I need to include the 3? The 3 doesn't change sign. It's always positive. Now, if that was a minus 3, I would include it because that's an important thing, because that does affect the result. But the plus 3 is not going to affect the sign of the result, because a plus times a minus is still a minus, a plus times a plus is still a plus. But if that was a minus 3, I would include it, because that does affect the result. So we stack them, we put our number line down, and we put our transition points, i.e. the zeros of the factors here. So we're going to have negative 3, negative 2, and positive 1. And they don't have to be correctly spaced. All you care about is the relationship between them. You don't have to have an evenly spaced number line there. Okay. To the left of negative 3, pick negative 4. All 3 of these are negative, which leads us to plus times minus, which is minus. Negative 2.5. Negative 2.5 looks like that. 0 seems like a good test value there. Plus 1 million seems like a good test value out here. So we get that. And I want to mark our zeros here. So negative 2 and negative 3, those are bad. That will cause division by 0 no matter what, so they should never be included. But positive 1, that's okay. We can include that if we need to. So let's look at what we're asked. We want positive or 0, greater than or equal to 0, compound inequality. So the first positive interval here is negative 3 to negative 2. If it was a polynomial inequality, we would automatically just include the endpoints. But this is a rational inequality, so we have to check. The negative 3 and the negative 2 cannot be included because they cause division by 0. So we'll leave parentheses there. And then union, we have to go 1 to infinity. And we look at 1, and 1 can be included. It's a 0 of the numerator, and that's okay. So that will be a bracket. Any questions on any step? So this is the end of chapter 4. So we're going to do our review on Tuesday, and our test on chapter 2 and 4 is next Thursday, a week from today. You excited? Seems a little easier than the trig ones to me. I can't wait to grade them. They should be faster to grade. All right, one more problem, and then we'll go out and celebrate with Cubs fans. So everything to one side, and here it makes more sense to put everything on the right-hand side. Minus 4. All right. Now that's not a fraction yet. We have to force that to be a fraction. What's the common denominator? X So we're going to multiply this middle term by x over x. That's going to be an x squared, and then I'm going to reorder it. Multiply that by x over x, we get minus 4x. This one already has an x in the denominator, so we have that. Oh, why do I have an equal? This should be greater than or equal to. This factors nicely. Okay. So now the zeros are just 0 and 2. And our factors, here we have to be a little careful. We have x minus 2 twice, right? And then we have x. And then we have our result. And the 0 in the denominator is the bad one. So that's bad, but 2 is okay. So when we go to do our sign chart, how about to the left of 0? So if we pick negative 1, that's to the left of 0. We get negative, 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 which is negative. If we pick 1, we get negative, negative, positive, which is positive. And then out here, it's all positive. Yeah. That's close. All right. So the question was, when is this expression less than or equal to 0? That expression is less than or equal to 0 from negative infinity to 0. And we exclude, we think we want to include because of the compound inequality, but we can't because that causes division by 0. So that is when that expression will be negative. Which some of you may have noticed right off the bat that that would be the answer, because isn't this numerator always, it's never negative, this numerator. So right, because of the square. So the only factor that affects this at all is just that x down there. So when that x is negative, the whole thing is negative. All right. See you next week. Week 12.
And we have tutoring tomorrow at 12.
Tutoring tomorrow at 12. Jessica's house.